Hello, everyone.
Okay.
Sorry,
yeah. Hi, everyone. Today we have a talk on Explainable Fuzzy System by Professor Jose Maria Alonso and Professor Corrado. And I just want to let you know about next webinar, which will be on July 3rd. The talk is going to be from learning to deep learning. So if you are interested in next talk, you can register for that. And today we're gonna listen to a talk from Professor Jose Maria. So now you can start.
Thank you very much, Sansani, for your introduction. First of all, I want to thank you for organizing this webinar. Also, I want to take profit of this time to introduce the task force on Explainable Fuzzy Systems. And in this regard, I want to thank to Professor Jesus Chamorro from the University of Granada, who invited me and encouraged me to start this task force a couple of years ago. We have now a good number of people involved in the task force with partners, members all around the world. And I'm really happy of the number of activities that we are carrying out during this time. Corrado is the vice chair of this task force, so we are working together. We were collaborating a long time ago, and this is a very, very nice and productive task force. The goal of the task force is twofold. In one sense, we want to monitor the status of works around explainability all around the world in the general sense. You probably have heard a lot about explainable artificial intelligence. And the idea is how we can do that the contribution of the Fussy community can be recognized and can be seen as something that is a productive and powerful tool in the context of explainable artificial intelligence. Actually, it's interesting to have in mind that a long time ago, before nobody was talking about explainable artificial intelligence, I'm thinking about 20, 50 years ago, there was a lot of people in the Fussy community who were talking about computing with word, interpretability, accuracy trade-off, and there was many people that were active in this regard, as we will see later. The issue is that in the last 5 years, it has been like a big wave around explainable artificial intelligence. And what we notice is that the presence of researchers coming from the Fussy community is not so big as expected. So we need to do an effort to let other communities know about what Fascilogic can do in the context of explainable artificial intelligence. The kind of activities that we do every year in the Fussy IEEE conference or the World Congress on Computational Intelligence is organizing a special session, having tutorial. Also this year we are organizing a competition. So you are invited to come and to join us next month in the Fussy IEEE conference and to follow all these activities. We are also editing a special issue on the IEEE Computational Intelligence magazine that is now in the last part of the editing process. So we expect that the finally accepted paper will be published in the end of this year, around November, probably. And we are also monitoring different attempts, different initiatives for defining new standards, the standards of the IEEE Standard Association related to Fascilogic, but also new initiatives that go for defining guidelines and architectural framework for explainable artificial intelligence. So we strongly believe that people from the Fussy community can contribute a lot to this, and it's important that we have a place and a role in all these new initiatives. So this is the agenda for today. We will start talking about notation, principle, definitions around explainable artificial intelligence. This is going to be done by my colleague, Corrado Mencar. Then I will come back with some software Fussy technologies for explainable artificial intelligence, and we will end the webinar with critical consideration, open challenge, and question and answer. So I hope you can enjoy and feel free to make questions for us that we will be happy to answer at the end. So now I'm going to give the floor to Corrado, and you can go on with your part of the presentation.
Okay, thank you. I think I have to wait for Sansani. Oh, okay. Okay, sorry. Yes, this first part of the talk is devoted to give some general concepts about XAI and the role Fascilogic can play within. If we want to take a big picture of XAI, we can highlight 4 main points. The first one is that society has been recognizing artificial intelligence as one of the most strategic technologies of our century. And this is witnessed by the flourishing emergence of standards, regulations, as well as the daily innovations and continuous technological advances. As a second point, AI is driving a technological revolution, and by definition, revolutions radically change our life. But people must decide the extent to which they want to be impacted by AI and under which conditions. The third point is that any technological change is easier to accept if it is clear to understand. And since AI is increasingly employed in critical decisions, an invoked feature is that AI systems are capable to explain why a decision has been made. This gave rise to Explainable Artificial Intelligence as an endeavor to evolve modern AI to a new generation of systems that are capable of both generating decisions and explicitly explaining such decisions to users. Now, in order to give a clear perception on the impact of AI to real life, our recent work introduced the idea of bring your own algorithm, especially in healthcare scenarios, where patients can use personal devices that use patient data in order to provide some medical advice. This advice, however, may only partially overlap with the clinician's decisions, which can be made by different algorithms or by some standardized protocols. In the original paper, this scenario was referred to diabetes treatment. Now, this kind of situation may lead to some unproductive contestability, where clinicians could oppose to personal AI recommendations, thus generating tension between them and patients. Of course, in this scenario, the adoption of black box solution does not help, while an explainable AI can reduce conflicts. Nevertheless, as we will see throughout this webinar, explainability requires a careful design. In general, researchers and engineers in AI are facing new challenges due to the penetration of AI in all aspects of human life, especially the most critical. Bias, for example, is the effect of erroneous assumptions in machine learning, which, when unnoticed, can harm entire categories of people, especially minority groups. Moreover, when artificial agents are used to take decisions, like in autonomous vehicles, it is important to assign responsibility to people in the case of accidents and misconducts. Therefore, users, designers, policymakers, lawyers need to understand who is responsible for the behavior and the decisions made by autonomous and intelligent systems. The picture on the right is of a cargo rotary wing attack drone capable of autonomous kamikaze attacks. According to United Nations, in March 2020, a drone of this type autonomously decided to attack a target in Libya. It is not known if such an attack killed some people, yet this is a concrete example of AI that can harm people without a direct, deliberate decision by other people. More in general, AI can do wrong, either unintentionally or intentionally. When this happens, it is fundamental to find out why. Many institutions, including universities or high-tech companies like Microsoft, are establishing research labs to explicitly tackle these challenges that are under the acronym of FATE: fairness, accountability, transparency, and ethics. Of course, trust, accountability, and bias check can be facilitated if the explanations that a system should provide are tailored to the class of users they are directed to. When building intelligent systems, the class or the classes of users of these systems must always be kept in the design cycle. Different stakeholders need different languages to understand the system. In the picture, we'll see an example of attention maps as tools for generating classification explanations. Attention maps highlight the features, which in this case are image pixels, that mostly concur to the determination of a decision, in this case, a classification. While this type of explanation can be of some use to model designers, perhaps for model debugging, because you may notice that the same pixels concur to different classifications, this kind of explanation is of little use to other classes of users. The XAI program was initiated by DARPA in 2016 with a 5-year research program. In recent years, policymakers such as European Union with the GDPR, national agencies, scientific institutions such as ACM and IEEE are recognizing the new challenges of AI and are working towards the definition of principles, guidelines, and standards so as to promote the development of autonomous intelligent systems that help but do not harm people. Europe is in particular active in regulating the impact of AI to citizens. Recently, a new proposal has been issued by the European Commission for a regulation of ethical principles for the development, deployment, and the use of AI and robotics and related technologies, following some specific objectives, including to ensure that AI systems that are placed in the market are used safely and respect existing law on fundamental rights, to ensure legal certainty to facilitate investment and innovation, to enhance governance and effective enforcement of existing law on fundamental rights and safety requirements, and finally to facilitate the development of a single market of safe and trustworthy AI applications to prevent market fragmentation. The European Commission recognizes that the exercise of these fundamental rights, such as, for example, the right of a fair trial, could be hampered when AI systems are not sufficiently transparent, explainable, or documented. The proposal classifies as high risk those artificial intelligence systems that are intended to use in contexts where it is necessary to avoid adverse impacts or to retain public trust, as well as to ensure accountability and redress. On a more global level, GPA was launched in 2020 and very recently revamped after the last G7 as a worldwide initiative bringing together experts from science, industry, civil society, and so on to support research and activities on AI-related priorities. Now, the responsible development, including transparency and explainability, is at the core of the values of such an initiative. Finally, in China, a document called a Next Generation Artificial Intelligence Development Plan defines the national development strategy on AI and includes some guarantee measures that foster laws, regulations, and ethical norms to promote a responsible development of AI. Currently, as Jose anticipated, the IEEE Standards Association is working on 2 projects for a guideline and a standard for XAI systems, one promoted by the Computer Society, the other by the Computational Intelligence Society. In particular, the latter project, it is called the XAI for Achieving Clarity and Interpretability of AI Systems, which is started a few days ago. It aims to define requirements and constraints that need to be satisfied for an AI system to be recognized as explainable. From a scientific viewpoint, it is interesting to give the viewpoint by Miller on XAI. We recognize that explainable artificial intelligence is not just a branch of artificial intelligence, but it requires a multidisciplinary approach that also involves human-computer interaction and the social sciences, because human is in the loop, and the technical achievements of AI may not be enough to reach the objective of explainability. Always in accordance to Miller, explanation can be viewed as a cognitive and social process, as well as a product. Viewing as a product, an explanation is an answer to a why question. But there are many facets hidden in this definition. For example, a why question can be interpreted in different ways, such as asking for some efficient cause, like why planets are spherical, or some final cause, like why ball bearings are spherical. Also, most often than not, why questions are contrastive and implicitly require some counterfactuals. But we can assign an infinite number of counterfactuals to an answer. The choice of a good counterfactual must take into account the class of users, as well as some psychological aspects. In a recent talk of Ruth Byrne, a professor of cognitive science at the Trinity College of Dublin, she pointed out that different cognitive load when causal explanation and counterfactuals are used. This shows that the design of real-world explainable systems cannot ignore psychological aspects of the products of this system. Well before the rise of explainable artificial intelligence, both the computational intelligence and the artificial intelligence communities were working on the concept of interpretability of systems. But what is the relation between explainability and interpretability? There is no general agreement on the relations between these two terms, which range from being synonyms to being almost opposite concepts. Within the realm of explainable fuzzy systems, it is commonplace to see interpretability as an enabling feature for explainability. While the latter is the ability of answering why questions, this ability is often implemented by taking profit of the systems whose structure and behavior can be understood. So what do we mean by interpretability? Within interpretability, it is possible to distinguish two subconcepts: that of transparency, which is determined by the simulatability of behavior, the decomposability of the structure of a model into meaningful part, or algorithmic transparency, while post hoc interpretability is the ability of understanding the outcome and its inference process through some textual descriptions, local model, visual models, analogies, and so on. Now, a recommended approach to modeling is to start by using transparent models, such as linear models, decision trees, fuzzy rule-based systems, and so on, and switch to more flexible yet opaque models only if the accuracy requirements do not permit the adoption of transparent models. The use of transparent models is especially recommended in high-stakes applications because it is easier to check the inner workings of the model so as to promote trust in intelligent systems. A recent study on how humans judge machines, made by Cesar Hidalgo and colleagues, this study shows that people judge decisions differently if they were made by humans or by machines, with a tendency of being more critical to machines, especially in accidental scenarios or scenarios involving physical harm. Well, we believe that the use of transparent models could possibly ameliorate the social acceptance of machines in high-stakes applications. When opaque models are needed and explainability is a requirement to fulfill, current approaches basically augment the black box systems with some explanatory machinery, including feature analysis to detect the most important features that concur to the formation of a decision, or some kind of global reverse engineering of a black box model with a transparent model, or more commonly, as a local reverse engineering of a black box so as to explain a specific outcome with a white box model. Finally, black box systems could be modified so as to include some modules that are capable to produce some representation to inspect a model in order to have a partial understanding of its inner workings. In all cases, explanations should be evaluated. Explanation evaluation is not yet mature, although some recent works paved the way for a multi-level evaluation strategy, starting from a purely functionally grounded evaluation based on some well-defined metrics, which, however, may only partially capture the essence of explainability, to a more holistic approach grounded on applications, which calls for comparison between human and machines explanations in task-oriented experiments, possibly designed through randomized control trials. In this context, how do we locate fuzzy logic in XAI? The main assumption is that fuzzy logic in general and fuzzy set theory in particular offers a mathematical underpinning to perception-based concepts, whereas such concepts are formed in human minds after perceiving some real phenomena, which vary in continuity. So concepts reflect the continuity of perceptions. We, as humans, often use natural language to express such concepts and their relations. So we believe that the fuzzy logic can be used to represent and process the semantics of natural language expressions. And since natural language is a powerful tool for providing explanations, then fuzzy logic can play an important role in explainable artificial intelligence. Historically, much of the research was devoted to interpretability of fuzzy systems, which is now intended as an enabling feature for explainability. In the past, it was believed that the mere use of fuzzy logic to design systems was a guarantee of interpretability. And still today, sometimes we find this assertion in scientific work, especially in a non-specialized literature. The fact is that fuzzy systems, that are systems designed by using the constructs of fuzzy logic, are not interpretable per se, in particular when the design is data-driven, as commonly occurs. We can say that the class of interpretable fuzzy systems is itself a rather specific fuzzy set in the universe of fuzzy systems. A peculiarity of the study of interpretability of fuzzy systems stands in the fact that fuzzy sets model the semantics of linguistic terms that are usually drawn from natural language. As a consequence, for each term, we can envision two semantical associations. An explicit semantics represented by fuzzy sets, fuzzy operators, etc., and an implicit semantics that is recalled in human's mind when the term is used. Matching these two semantics, what is called semantical intention, is at the very core of research in interpretable fuzzy systems. More in general, interpretability in fuzzy systems is identified with semantical intention, which is also known as comprehensibility, and completed with readability, that is a set of properties mostly related to the structural complexity of a fuzzy model, which takes into account the limited cognitive abilities of a human brain to keep information chunks in short-term memory. Interpretability in the fuzzy systems is partially formalized through a set of constraints on the different levels of fuzzy systems, including fuzzy sets, fuzzy rules, and so on. And there is not an unanimously accepted set of constraints, so each designer chooses a set according to the application context, their background knowledge, or their preference. There are tens of such interpretability constraints in the literature. Finally, from a methodological side, several approaches have been proposed to design interpretable fuzzy systems. A classical approach starts with an initial fuzzy system designed for interpretability, which is eventually fine-tuned to improve accuracy. But the reverse is also true. We have accuracy-driven fuzzy systems that are modified so as to fulfill some interpretability criteria without sacrificing too much of accuracy. Other approaches recognize the conflicting objectives of interpretability and accuracy and use multi-objective approaches, which are often genetic but not always, to carry out some Pareto fronts of systems from which the final solution is eventually selected. Finally, some ad hoc techniques exist, which design fuzzy system from data by taking into account some interpretability constraints in the induction algorithm itself. Well, here the first part of the webinar terminates. The next part is devoted to an overview of fuzzy technology for explainable artificial intelligence by Jose. I think that I can stop here.
Yes, I think that now I should share my screen. I don't know if you can see my screen now.
Okay.
Now,
yes.
Okay. Well, after this general view of explainable artificial intelligence and how fuzzy logic can play a role in the context of explainability, and especially with this idea of interpretability as an enabling element or an enabling technology for going for explainability, let's go on with the fuzzy set and system fit. Well, as I told at the beginning, there were many works in the community of Fascilogic dealing with interpretability of fuzzy systems. Actually, if we go back at the beginning, even in 1965 and the first controllers in the 70s, these systems were supposed to be inherently explainable or interpretable in the sense that they were carefully designed by humans for humans. And the idea was that there was a person, a knowledge engineer, a human who was designing every linguistic term, every rule. So at the end, you have a system that was simple, but easy to understand. So in practice, when we are thinking about having a system that can be interpretable, and then we can enable around that interpretable system the explainability that humans could require, we need to do something else. We need to move from interpretable fuzzy system to explainable fuzzy system. And how can we do that? The situation is that a long time ago, we passed from expert system to data-driven system. And when we go to data-driven system, the issue is that system automatically learn from data can become a black box, because if you are not establishing any kind of a careful constraint, the system can just only focus on accuracy and disregard absolutely all idea of interpretability. Because of this, Corrado already emphasized the point that using fuzzy system is not enough to have an interpretable system. We need to be careful with the constraints that we want to impose in the system. But if we are able to learn from data in the same way that we were able to design expert with knowledge coming from an expert, we can formalize, no matter if the knowledge is coming from an expert or is coming from data, the information that we have in a precise natural language that is later represented by a formalist, a mathematical formalist that is grounded in the Fascilogic theory. And this makes us possible to use this kind of inference to pass from input to output, but also to make reasoning in a way that we can, at the end, when we have an output, to go to the reverse path and go to do an explanation to the user. And this explanation should be feasible no matter if the knowledge that we have in this knowledge base, all the rule bases, all the linguistic terms were properly defined, grounded in semantics, then it would be possible to do this linguistic explanation. When we are talking about interpretability, we are showing the description of the system to the user, and the user has to make their own interpretation. While when we talk about explainability, our idea of explainability is that we have explainability on top of interpretability. So if we are able to manage a natural description where we are using a number of structural constraints, keeping a system that is simple enough and transparent and readable, but at the same time, we pay attention to semantic constraints, to co-intensive approach, like Corrado was referring before. We have the issue of having a system that is not only transparent, but is also understandable. And with that, we can have something that is a system with pieces of information that we can convey and we can communicate to you. And this is not something that is new. It's something that is coming back to the 80s when, for example, Michalski was proposing this comprehensibility postulate and was making reference to the need to represent the information in a way that is symbolic and that is semantically grounded in order that it can be understood by humans. What we want to do is to take profit of this linguistic interface, this linguistic representation that we have with fuzzy system, in order to make the jump from the formalist representation of rules and fuzzy partitions into a natural narrative in natural language that is easy to read and easy to understand. Then the challenge is how we can do that. In order to do that, in order to go to the communication to the user, we need to think about human matching communication, human matching interaction. And for that, it's important to think about how to make an effective communication. This is something that is there in the literature from a long time ago. We have many different principles, many issues that we should keep in mind. If we want to establish a discourse that can be understandable, that can be at the end, something that people can grasp and can consider that was satisfactory one and was useful to understand what's the system output and even more how the system behaves and arrives to this output. Well, regarding the relation between natural language and fuzzy logic, again, we have many different contributions. Probably the most important one was the original from Lofty-Thade when establishing the idea of going from computer with numbers to computing with words and trying to pass from systems that were just only considering numbers to systems that were able to manage words in themselves. And in some sense, this was the idea that in an intuitive way, someone could describe with words the behavior of a machine, for example, and we could formalize this behavior in a set of rules that describe how the machine works. And at the end, we can make reasoning and we can now do explanation about how the machine is working. At the beginning, this kind of technology was used for doing linguistic description from data, for example. There are works that try to describe in natural language the weather forecast, for example. Look into the numbers, look into the prediction, look into the weather forecast, how we can communicate this to humans in a language that most people, most audience can understand. And this is important because we need to think about which is our audience. And when we are thinking about explainability, we need to think who is the person who is to receive the explanation. Because depending on the background, depending on the preference, depending on the knowledge of this person, we could need to do explanations in a way or another. Here, I want to refer to this special issue on the IEEE Computational Intelligence magazine, where we were co-editing a special issue on natural language generation with computational intelligence. It's true that in the Fussy community, there were a number of researchers working in generating linguistic description from data, but it's also true that there is another community in the computational linguistic field that has also a long tradition in generating natural language. And in this special issue, we try to put together both communities and look for synergies. So if you are interested in this, I recommend you to go to this special issue and pay attention or take a look to the papers that were published. Well, now we know how we can build an interpretable system, how we can establish a number of constraints from the point of view of complexity, but also from the point of view of semantic interpretability or understandability. And the question is how to build the explainable fuzzy system that is taking profit of this interpretability. For that, it's not that we need, again, to invent or to make up with something totally new. No, we can make profit of all the research that has been done before. So we have a lot of work regarding knowledge representation. And you can see a really nice paper from the and Prada that they were thinking about the semantic of rules and how they can express different meanings depending on the fuzzy operator that we use. How we are implementing and or connectives, how we are doing the implication. There are many works regarding that. We have the work regarding computing with words and computing with perception, but we also have work related to fuzzy ontologies and fuzzy cognitive maps that are looking to how to represent knowledge in the sense that at the end it's not only just something that is emerging from data, but we have a formalist to represent the knowledge that is provided by a user, by an expert, or that is extracted from a source where this knowledge could be a structure or non-structure. It doesn't matter if it is already in an ontology or we are extracting this information from Wikipedia, for example. Let's see the technology, but we have a lot of technology in Fascilogic for doing that. Also, it's important to pay attention to fuzzy reasoning. And regarding fuzzy reasoning, is the question that we can do deduction, abduction, induction. There are different ways to reason with fuzzy concepts. And fuzzy concepts are there in the reality. Most of the things that are surrounding us are fuzzy. We know that language is baked by nature. It's not just black and white. There is some degrees that we need to handle and to manage if we want to represent all this information in the proper. And of course, we cannot forget all the work that has been done around evolutionary fuzzy system. Evolutionary fuzzy system, this is a paper that was published in the IEEE Computational Intelligence and Magazines too, and is providing a very nice overview of this field of research, was doing a lot of work regarding how to build interpretability accuracy traits and how to use evolutionary techniques in order to provide the user not only with one fuzzy system, but with a collection or a family of solutions where the user at the end needs to look for the trade-off, look for the best solution for their specific problem. Well, let's go now to our approach, how we are trying to propose or trying to build explainable fuzzy system. In our view, the idea of building an explainable fuzzy system with explainability on top of interpretability implies that we want to combine in a knowledge base information coming from an expert or from an ontology and information coming from data. And the way how we can extract information from data and to learn from data implies that we can use tools from Fascilogic, but also for other computational intelligence techniques. Keep in mind that the idea of computational intelligence is that we have Fascilogic, evolutionary computation, neural network, probability reasoning, and all of them can work together. This was the idea of the hammer principle by Loftus, and not use only one single tool. Try to use the one that is better for you in every moment, depending on the conditions, depending on the problem that you want to solve. And now the issue is that if we are able to have a system that is transparent, that is interpretable, that lets us to understand how the system is making this analysis of the information that we are observing in reality, we will be able to reproduce this interpretation in an automatic way, in the sense that we can create a system that is making the interpretation for us. Of course, if we are expert in Fascilogic, maybe for us it's enough to pay attention to take a look to the rules, and we can understand how the rules work if they were properly designed, for sure. If we have experience working with Bayesian network, maybe we prefer to take a look to a Bayesian network, or maybe we prefer decision trees, or maybe we prefer differential equation. It doesn't matter. The background, the expertise of the user is making an emphasis on the model that this person could prefer. That's clear. But when we go not to expert public, when we go to the general public, and we want to explain, for example, to a physician, to a doctor, or we want to explain to a kid, to our child, or to our grandmother how something is working, then it's not possible just to show a set of rules or to show the mathematical model and say, look, this is interpretable because it is satisfying a number of constraints, it's easy to interpret, so you can understand what it's doing. This is true if you have some background to be able to do the interpretation. Otherwise, you cannot do this interpretation. So our idea of explainability is how we can make an automatic interpretation of this information, and we can provide this explanation in terms of a linguistic description of how the system works. And of course, when we were at the beginning working on the idea of linguistic description of data, we were doing automatic reporting. So we have just a report describing how the system works. But here, this is not enough. The idea is that when we are explaining something, and if you are a teacher, if you have tried to explain something, how something works, you will see that humans are not satisfied just with a single one-shot explanation. Usually, explanations require some interactivity. We are given some pieces of information, and depending on the reaction, depending on the feedback of the audience, maybe this is enough, or maybe we need to change our explanation. We have to try to give additional pieces of information, or we have to explain the same thing in a different way. So think that we have this kind of loop, that is this idea of interactivity, where we are able to combine techniques for natural language generation and then techniques for natural language understanding. This is similar to what you can see nowadays with chatbots, Siri, Cortana, whatever, that are more and more available and popular technologies all around us. So the idea is that we could use these technologies as ability technologies to build our explainable system. So we have our interpretable fuzzy system, we have human-computer interaction, and the nexus or the link between human and machine requires using natural language processing techniques for understanding and for generation. And in this context, we use a number of software tools that we have been developing during the years. In fact, the first tool that I want to tell about is this software that is called Waje. This is an open source software that was originally designed for building interpretable fuzzy systems. The idea of this interpretable fuzzy system was that we were imposing the use of strong fuzzy partitions, a number of constraints, and we were able to create a partition that was in accordance or in agreement with the data distribution. Then if we have a user that is able to describe the granularity of the problem, a number of linguistic terms, we could select the right partition. We could also even tune or change this partition more in agreement with the semantic grounding of the user to be able that we are satisfying this idea of semantical intention that is very important. Imagine that if we are two humans talking one each other, and each of us has a different background, different conception, different ideas, we are not going to understand each other. We need to have a common ground. And this common ground is what happens when we have a communication protocol to establish which is in common between us. And when we agree in this meaning of the concept, we have the semantic grounded, then the communication is possible. So with this kind of software, we can learn partitions, we can learn rules from data, but we can also define by hand these rules or this partition if we have expert knowledge to do that. We can also see how good is the system, how the inference is done in the usual way of fuzzy inference, but also we have this representation, this graphical representation that reminds social networks, and that is called fingrams. This is a way to represent the interaction between fuzzy rules and how rules are more or less representative in the rule base depending on the node that is representing the rule, with bigger size when the rule is more important, smaller size when it's less important, and also we have connection between those rules that are firing at the same time. But what we have done more recently is trying to add this idea of explainability on top of the system that we have built, and then we are able to generate this linguistic description, this linguistic explanation, where we translate the inference that is doing by the software into a narrative in natural language, where we say which is the output, and we try to provide the user with an explanation in terms of the rules that were fired, which was the degree of firing, if there were just one winner rule or several rules fired with similar degrees. And this is information that we can try to provide to the user in order to make the user trust better on the software tool that we are using. Of course, this can be with complementary graphical techniques. The part related to linguistic description that we are using is used in connection with this software that was LDCP. This was originally defined or designed to think about the linguistic description of data. but now it's totally integrated with WAG. So when WAG is generating this linguistic explanation, is making calls to this software and using a number of templates, dynamic templates to generate the explanation for different problems in an automatic way. You can go for this software that is open source. You also can take a look to the related reference. The other software that I want to show you or to invite you to use is this library that is called Java Fuzzy Markup Language, that is available not only in Java but also in Python, and that is the first library that is implementing the IEEE standard for fuzzy markup language. This was the first attempt of the fuzzy community to have a standard to make interoperable different software tools in order to have the opportunity that a fuzzy system that was generated, that was tuned with one specific software, could be later refined or used by another software. So in this case, what we have behind WAG and behind other tools that we are using is this interoperability that is enabled thanks to the use of this fuzzy markup language library that is making possible this communication. And in fact, this is the same idea that we have with this other software. This was done more recently, and it's a web service that is connected to Weka. Maybe some of you have already used Weka. Weka is a well-known software, open source software too, for classification, for regression, for different tasks, and data mining in general. There are many different algorithms implemented there, not only fuzzy system, but also fuzzy system like Furia, that is fuzzy and order rule induction algorithm. And the idea is that here in Split class, we have implemented a number of algorithms that are not the algorithm, we implemented the bridge between our web service and Weka in order to take profit of the algorithms that are already developed, that are already implemented in Weka. And what we are doing here is trying to improve or to enhance the multimodal explanation, the way how we convey the information of these different algorithms to the user, with a visual representation. For example, here you can see a tree, and below we have linguistic description associated to the tree. The same is done when we have fuzzy rules. And these explanations are textual plus visual, but also global plus local explanation. When we are talking about local explanations, we are thinking about how to explain the classification of a single data instance. And when we are talking about global explanation, we are talking about the global behavior of the system. So think about things like the confusion matrix. When you have a classifier, you can see that there are some classes that are better classified than others, and there are classes that are not so easy to manage. Well, let's see a couple of examples of application in the medical domain. The medical domain is the prototypical example of application where humans require explanations. We could have a machine that is giving decision support to a physician, but it's very important in order that the physician can trust the recommendation of the decision of the machine, that they is able to provide an explanation. So in this example, we have a program that we were developing, combining expert knowledge and ontology and using WAG in order to combine fuzzy partitions, rule generated by expert and from data to put all together and to make this diagnosis. So you can see here the idea that we can use this software to build an interpretable system. Okay, we were just only focused on interpretability. Another example of application where we go from interpretability to explainability is this other example of Alzheimer's disease diagnosis. In this case, we did something similar to the previous example, but we did a step ahead. We go farther from interpretability. We combine the information that we were generated with software like WAG, but also with the split class, and then we build different models with different granularity, paying attention to different sources of information, visual information, cognitive score, demographic, genotype data, whatever. And for each of these different sources of information, we were building different models that were able to provide different but complementary explanation. And the common thing to all of them is that these explanations are visual. We have a way to represent or to visualize the model, but are also textual, because we have the opportunity to have this linguistic layer on top of all these models that in practice is a linguistic fuzzy system that is making an approximation of the model that is behind, and that is represented using the standard for IEEE fuzzy markup. Well, till now, I was talking about factual explanation. So we observe the reality and we try to explain what happened in reality. Another thing that is very important and that Corrado was already introducing is the idea of contrastiveness or counterfactuality. And in that sense, I recommend you to take a look to this book by Judy Appel, that is the book of why, where he is explaining the difference between causality and correlation, and he is enumerating a number of important issues about why questions. Why questions are usually contrastive. They can be represented in different ways, but all of them has in common the idea that while when we are talking about factual explanations, we observe the reality. And if we are able to understand the reality, we can interact, we can do something to change the reality. We have the dimension of imagine. When we are thinking to imagine, and we are just in the top of this plot that you can see here on the right, you see that the idea of imagine is that humans think about what could happen if we were doing or we were acting in a different way. And this is what is behind the idea of counterfactual. So we can have a system, we know what the system do, this is the factual explanation, but we can challenge the system, we can wonder, we can try to simulate different scenarios, different situations, and try to anticipate how the system will behave in a different situation. We did recently this work in which we were doing a survey of different work on factual and counterfactual explanations. And I would like to summarize some of the findings that we have. And is that, for example, most of the work related to counterfactuals, they are dealing with some way causal relations. They are thinking about mainly about classification, not all other tasks. So there is a lot of room here of work to think about counterfactuality in many different tasks that are usual in machine learning, in artificial intelligence in general. We have also the difference between counterfactual explanation for model-specific or model-agnostic models. And also the issue is the counterfactual is able to manage numerical, linguistic, visual information. In general, we would like to manage multimodal information, but most of the systems nowadays are working with numeric information. So if you are interested in this kind of work, there is a lot of work to be done here. Also, regarding the evaluation, as Corrado already said, it's very important to go for human evaluation. And most of the work nowadays, they have only metrics that are considered objectives because they are mainly data-driven metrics, but they are not making evaluation with humans. And if we are explaining to humans, it's essential that we think about how to make an experiment, thinking about psycholinguistics, and try to anticipate and then to validate and to evaluate the goodness of the explanation for humans. Let's see an example where we were creating this kind of factual and counterfactual explanations. This is a simple problem, but it's a real problem that is related to beer style classification, where the idea is that given a beer, we can try to describe the beer style in terms of three attributes that are color, bitterness, and strength, or the alcohol level. And this is something that is admitted and is well known by experts. So we could talk to people who are able to describe us in terms of color, bitterness, and strength, which is the type of beer. We can consider people with different background, more expert or non-expert, but this is something that is interesting, and that when we wanted to do a human evaluation, you can ask people to go for the evaluation, and people is willing to take part. This is the data set that we were managing. This is a simple and a small data set, but not so simple in the sense that we have 8 different classes, what means that the classification task is quite challenging. But it's simple in the sense that we have only 3 attributes, what means that we are able to make a representation of the data in 3 dimensions. This is very useful because we can try to see exactly how the system works in reality without needing to do any kind of dimensionality reduction where we could lost information, for example, with PCA. So in this case, we prefer to have this system with only 3 features, but 3 features that are meaningful for the audience we are working on. And we create classifiers with different decision trees and with different rule-based systems. At the end, imagine that we have a decision tree like this. We can try to analyze which is the branch of the tree that is activated for a single data instance, and we can read information in the tree. What we do is to put a linguistic layer on top, and this linguistic layer is in practice a fuzzy system that is translated these numerical values through the use of this kind of linguistic terms in a fuzzy partition in a narrative like this, where we can say which is the output class, why is this output. This will be the first part, that is the factual explanation. And then at the end, we have the counterfactual explanation. That is how could be another different VR style if something were different in the VR that we have. Okay. The challenging thing is that we are able to implement this like an interactive system where the user can decide, okay, I may not agree with, I don't agree with the class that you are suggesting. Why not this other class? And then the system needs to figure out why and look for the counterfactual that is more suitable, more relevant for that question. This is something that we did, that we implemented with the software that we have. For example, with XP class, we compare the accuracy of different models, not only in terms of accuracy, but in terms also of the kind of linguistic explanation that they are able to generate. And then the models that we could compare visually, but we could also export these models, taking profit of the standard of IEEE for Fuzzy Systems to WAGE, and then open the system again in WAGE in order to see how the inference was done and try to see which were the rules that were fired, how these rules were interacting between them, and describing this kind of linguistic description and linguistic explanation. Well, all these kind of things are letting us to make this interpretable and then explainable system. And now it's time for human evaluation. So we are right now doing a human evaluation of these classifiers that we were generating. So I invite you, if you are interested to collaborate with us and to contribute to this study, to go to this URL and answer to this poll where we are presenting different factual and counterfactual explanations. And we are asking you to rate what's your opinion about the informativeness, trustworthiness, accuracy, relevance of each of the potential counterfactuals. So on the left, you see the factual explanation, some alternative counterfactual with different methods, and then the question is try to figure out which one of these methods could be better or not in order to validate the hypothesis that is behind of this experimental empirical study. Well, that's all for my part. Now we are going to pass again to my colleague, Corrado Mencar, to ending the webinar with some critical consideration and open challenge.
Okay. Yes, XAI is a relatively young research subject. Even if research on interpretable machine learning and interpretable fuzzy systems have about 3 or more decades of history, XAI opened the discussion into new directions with generated debates and open challenges. And the first critical consideration is on the very definition of explainability. Interestingly, in-depth studies on this concept often point to the old idea of causality. Jose already anticipated many of the things here. But if an explanation is an answer to a why question, then such an answer often requires a causal chain, which must be properly composed of the events that led to the outcome. This opens the door to a number of challenges. The most important one is that machine learning systems only catch correlations, while building a correct causal model requires an intervention on the environment in order to discover cause and effect relations. Transparent models can help to define the efficient causes that produce an outcome. For this reason, transparent models are of great value in XAI, especially in high-stakes applications. Yet, these efficient causes pertain to the model, not necessarily to the modeled phenomenon. Furthermore, a complete causal chain can be very complex even for simple models. How to choose the most valuable causes is also an open challenge, which naturally entails the support of psychological studies. Also, there are different modes of causality: efficient, final, materials, formal, and so on. And this should be properly recognized. Finally, an emerging issue arises because XAI solutions are penetrating the market. And this issue is on deceptive explanations. That is, fake explanations that seem convincing to the user, but hide the real causes that produce an outcome, perhaps because they involve some sensitive information, such as race. Here again, transparent models are better subject to scrutiny, but transparency could be conflictual with business interests. Another key aspect is about assessing explainability. The picture on the right shows how complex the process of evaluating explainability can be, because an explanation involves a complex cognitive process. There are several phases to evaluate. We recently proposed the one metric for evaluating the descriptive stability of induction methods for rule-based systems. But many works proposing XA solutions mainly focus on some structural criteria and leave the appreciation of explainability to the subjective evaluation of the readers. It is important that the evaluation of explainable systems should carry out with the aid of experimenters that have specific skills on human-based assessment. Also, randomized control trials can be a valid help for a fair evaluation of explainability, especially for testing comprehension and explanation, comprehension of explanation and performance improvement. As a final remark, more focused on explainable fuzzy systems, ongoing research is on design methodologies of all their components, as also Jose anticipated, in order to produce semantically grounded explanations, interactive and multimodal interfaces, as well as novel forms of knowledge representation to manage complex relations in human comprehensible forms. This requires to join forces among artificial intelligence, especially machine learning and Fascilogic communities. The cloud image in the slide shows the cross-citation relation among scholars publishing papers with keywords related to explainability, interpretability, and similar. The cloud was generated in 2018 and shows that there exist separate communities of scholars working on the same subject. Things may have changed since 2018, but perhaps not too much. The road, we are convinced that the road for strengthening collaborations can be shortened by promoting the development of open software for explainable fuzzy systems and XAI in general, as well as guidelines and widely accepted standards. Well, you will find the reference to some works that inspired this webinar throughout the presentation. Here, some recent works of ours are collected for further references. Many of the concepts that have been reported can be found in our recent book on explainable fuzzy systems, published by Springer. And this closes our presentation. Thank you very much.
Okay, thank you. Thank you for the talk. And I have some questions that you want to ask. The first question is from Tusha. The question is, what is fuzzy logic and fuzzy system?
Quite a wide question.
Yeah.
May I, Jose, should I answer myself?
Yeah, you can. We were not talking about this because we considered that because of the audience, it was something general.
Yes, perhaps we were taking it for granted, but it is a corpus of theories and methodologies that are capable to model the semantics of perception-based concepts. That is, concepts that are acquired by humans through perceptions and are usually expressed in natural language. For example, today is, for example, in my city is very hot. Hot is a perception-based concept that we can model with fuzzy logic. And fuzzy systems are predictive systems, classification systems, or regression systems, which are based on this kind of theory. It's a very, very general answer. Sorry, I cannot be more precise. You may write us for, because, well, there are entire courses on fuzzy logic. It's not easy to condense it.
The general definition, sorry, Corrado, is to think about Boolean logic versus fuzzy logic. So probably he knows about Boolean logic. In Boolean logic, we have true or false. In fuzzy logic, we have infinite degrees between false and true. Of course, there are also multivariate logic with different levels. But in practice, this is the main issue, that we are able to have a degree of firing, a degree of membership to each of the elements. And with this notion, we are able to describe concepts, as Corrado said, and goes to describe the behavior of system.
Yeah. Yes. Okay. Next question is from Bruno Stefano. He asking if you two plan are you two planning to be active in IEEE-CIS WGP 2976? It's not related to the talk, but
I don't know what he means by this. I don't know what is related. What we were talking is that I know that Bruno is also involved with some of the standards, and we are monitoring from the IEEE Task Force on the activities that are doing in the community around different standards. And I think that is very important that all the communities that are in the Computational Intelligence Society are taking part, not only Fussy community, but also neural network, evolutionary computation.
Okay.
We try to emphasize and to describe in the presentation that this is a very multidisciplinary field, where it's important that everyone can contribute with different and complementary perspectives.
Okay. And next question is how cognitive behavioral can be achieved by fuzzy system?
Well, regarding cognitive behavior, this is something that is challenging, that this is something that is related to social science too. In the context of Fascilogic, the first thing that you can think about is the idea of fuzzy cognitive math, for example. Is one part of research in fuzzy set and system that was paying attention to this idea of how to represent cognitive concepts. That's one thing. The other is that in social science, in cognitive science in general, there are many concepts that are coming in natural world that are vague by nature and fuzzy in some way. And the way to formalize these concepts and to manage and handle these concepts requires any mathematical formalism that Fascilogic is quite well prepared for that. I don't know, Corrado, if you want to add something.
Yeah, just to add something more, if you read papers on explainable artificial intelligence, some of them rely on psychological experiments, social experiments, and the results of these experiments are used to reproduce some behaviors on the machine. This is why in explainable artificial intelligence are multidisciplinary. You just cannot imagine how a person could behave. You have to see with the experiment what is a behavior, what is, for example, the cognitive load of an explanation, which if it is made by only by counterfactuals or by complex counterfactuals or causal explanations. And in order to then you use these results in order to produce systems that are capable to generate explanation as people may expect. And finally, the class of user is also important. One thing is produce explanation for model designers, another is for lay users, for example. So I think there is a tight connection with the psychology and cognitive science from the experimental side.
Okay. I think this is going to be last question. Last question is, how do we implement Fussy project in Python?
Well, actually, right now, we have a wrapper of the Java library for the standard that is already working in Python. So that means that like other programs that you have in Python are not natively implemented in Python, but is calling to Java program that already exists. Of course, it is possible just to try to reproduce and to program in Python because Python is object-oriented programming like Java. But if you have a software that is already implemented, it makes no sense to repeat the effort. Anyway, I know that there are also some initiatives to implement new software, Fussy software on Python that you can see the Fussy System Software Task Force, where I've been also involved for a long time ago. There is a very nice website where you can see different software available. And if sometime before there were many software, at the beginning, the most popular software for most engineers was MATLAB. Then there were many tools in Java, and now there are many tools in Python, and there are more and more Fussy system software also available in Python. So it is possible to code, and it's possible to use even tools that already exist.
Okay. So thank you very much, both of you. Oh,
thank you to the audience.
I have another question. Do you want to answer the last question? It's just coming. The last question is the explanation unique or continuous and continuous?
No, there is not a unique explanation because the situation is that the explanation depends on the person who is going to receive the explanation. So we have to analyze the situation, we have to analyze the context, and depending on the situation, depending on the experience of the user, depending on who is going to receive the explanation, we can have different explanations. And the question is, which is the right explanation? Which is the best explanation for a specific user? This is very challenging. You can have a ranking of relevance of different explanations. It's factual and counterfactual. It's like when you are in Google and you are looking for information retrieval, you look for a website, you have a set of potential links. In here, we have something similar. You can figure out different explanations. The question is, which one is better or worse for different users? You can have one main explanation and think about different ways of representing the explanation in different levels of details of different granularity, but it's the same explanation. Or you can have alternative complementary explanation. For example, if you are thinking about tabular data and we have different features in a data set, you can have a system that is depending on a number of features, but another system that depends on another number of features. And then you can elaborate different explanations, paying attention to different properties that are equivalent or that could be trying to justify the same thing, but are totally different, are not exactly the same explanation.
Okay.
And may I add just to complete, the generation of explanation only also depends on the knowledge base. And in fact, the methods can generate different knowledge bases according to some hidden parameters or random values. In fact, we studied the descriptive stability, that is, how a method is capable of generating almost the same knowledge base, and this means the same explanations of giving the same context, or if these methods vary the knowledge bases according to some hidden parameters. This is what we call the descriptive stability, and we have just published a paper on the last conference of IEEE.
Okay, thank you so much, both of you. I think we ran out of time, so if there is any question, you can write an email to Professor Alonso or Professor Corrado. Okay.
For sure. Thank you very much.
Thank you very much for coming. So I'm just gonna end today. Thank you so much for coming.
Bye
bye.
Thank you.
Bye.
Bye bye. Good night.
You too.